So, welcome to this session of the lecture on dielectric slab guides. So, this is a very important structure which is used for all substrate based circuits and antennas, because we all know the importance of the dielectric substrate in antenna design and microwave circuit design. For antenna design, for example, we are extremely concerned with things like surface wave modes, how much power does the surface wave extract, which is directly revealed or directly manifested in the back radiation characteristics of the antenna. In many cases, we want to suppress surface wave modes by using engineered substrates. But before all these things, we need a physical understanding as to what is going on inside the substrate. What are particularly the modes which are excited in the substrate, number one. How to calculate the propagation characteristics of such modes. What are the cutoff frequencies of such modes. And particularly what happens, so to say, below cutoff and above cutoff for the dielectric slab. So, this will lead to a very important and a very comprehensive and detailed understanding about the behavior of a dielectric slab, which is almost omnipresent in any kind of planar microwave circuit design, be it be antennas or be it be microwave circuits. So, therefore, let us go to the analysis of such structures. So, this is the dielectric slab guide, which means that we have a dielectric slab this is my x direction and this is my z direction. And the width of the slab is A. So, this is my dielectric slab, the yellow shaded region. Its permittivity and permeability are epsilon d mu d, and as we always use, the permittivity and permeability of the medium above, which is free space, the medium above and below, which is free space, is epsilon naught mu naught. So, first of all, it is important to understand that we do not always need conductors for the guidance of electromagnetic waves. Dielectric slabs perform also the function of guidance of electromagnetic waves, but with a difference, because in addition to the waves being guided in this region, the waves will also be radiated in such a region, or it will exist in that region, because these two surfaces are dielectric to air interfaces. So, therefore, the fields will be continuous between this region and this region. So, there will be fields which will be existing here and the fields which will be existing here. So, we shall consider this problem to be a two dimensional problem, allowing no variation with the y coordinate. Okay. So, therefore, along the y direction we will assume that there is no variation of electromagnetic field. So, it is desired now to find the z travelling waves, that is the waves travelling along the z direction with a e to the power minus j kz z variation. So, the variation in this direction will be of the form e to the power minus j So, the waves in this direction are going to have a variation of e to the power minus j k z z. So, modes either T and Tm to either x or z can be found. So, modes T and Tm to either x or z can be found, and we will choose the T and Tm to z modes. Okay, because the propagation is along the z direction. So, for the modes which are Tm to z, let us write down for modes which are Tm to z, we already know for the modes which are Tm to z, we already know its field distribution, because we have studied such modes in the case of the rectangular waveguide, and we have found that such modes are generated when A equal to u z psi, number 1, this is not new to us, and the corresponding magnetic field distributions are given by H x equal to del psi del y H y equal to minus del psi del x and H z equal to 0, whence the name Tm to z mode. This is also not new to us, we have derived all these equations before. We have also found out the corresponding electric fields for the Tm to z mode, and which were E x is equal to 1 by j omega epsilon del square psi del x del z E y equal to 1 by j omega epsilon del square psi del y del z and E z equal to 1 by j omega epsilon del square del z square plus k square psi. So, this equation also we have studied before. So, all these are the field distribution of the Tm to z mode. But for the current case, we have del del y equal to 0. So, for the current case, we have no variation along the y. So, we have del del y equal to 0, and for the e to the power minus j k z z variation along the z direction, we have del del z as minus j k z. Therefore, equation number 2 and 3 can be written now as E x is minus k z by omega epsilon del psi del x E y becomes 0 because del del y is 0, E z becomes 1 by j omega epsilon k square minus k z square psi, pretty much the same thing we derived before because the del z variation there too was e to the power minus, because the z variation there too was e to the power minus j k z z. So, del z was minus j k z. So, E z becomes this, H x becomes 0 because del psi del y becomes 0, H y is unaffected, it is minus del psi del x. So, these are the 3 field components under these 2 conditions. So, these are the 3 field components under these 2 conditions pertaining to the dielectric slab. Now, we shall consider 2 cases separately. One, the psi is an odd function of x which is denoted by psi o. So, one condition will be psi is an odd function of x denoted by psi odd, psi o, o stands for odd, and 2, psi is an even function of x denoted by psi e. So, these are the 2 possible distributions of psi we will consider. So, for the odd case, so for this case we can choose in the dielectric region, that is psi d o, d stands for inside the dielectric slab, o stands for odd mode, that is a sin u x e to the power minus j k z z for mod x less than a by 2. So, this is equation 5. So, you see this is an odd distribution, an odd function of x, and in the air region. So, this is in the dielectric region, and in the air region we have psi A odd, A stands for air, O stands for odd again, B e to the power minus V x, because the fields are decaying along the x direction, e to the power minus j k z z for x greater than a by 2, and psi a 0 and psi a 0 is minus b e to the power v x e to the power minus j k z z for x is lesser than minus a by 2, for x is lesser than minus a by 2. Okay, so these are this plus b and minus b are chosen in order to match the fields across the air dielectric interface at x equal to a by 2 and x equal to minus a by 2. So, which are this region and this region. So, this is x equal to plus a by 2 and this is x equal to minus a by 2. So, we are describing the fields here and here. Okay. So, the change in sign of V is to also ensure that the fields decay down to 0 when x equal to minus infinity, and here also for x greater than a by 2 it is e to the power minus v x, because we have to ensure that the fields decay down to 0 at x equal to plus infinity. So, therefore, these two signs have to obey the behavior of the waves at x equal to plus infinity and x equal to minus infinity respectively. So, now we can also write down the separation equation in each region. So, the separation equations become u square plus k z square equal to k d square, that is equal to mu omega square that is equal to omega square epsilon d mu d, that is inside the dielectric region. So, u is the eigen number along the x direction, k z is along the z direction, there is no variation along the y direction. So, the third eigen number is 0 or the third eigen value is 0, and we have k d square, which is the wave number inside the dielectric, the wave number squared inside the dielectric, so to say. And next we have the separation equation in the air region, which is minus v square plus k z square equal to k 0 square, that is equal to omega square epsilon naught mu naught. We call this previous equation, equation 6, so that we can now call this equation, equation 7. Okay. So, here for this equation we can write the variation along the x direction was e to the power minus v x, which could have which can be written as e to the power minus j v x So, is e to the power minus v x, which can be written as e to the power minus j times minus j v x and therefore, when we squared this eigen number up. So, it is minus j v whole square. So, it becomes minus v square. So, that is how we have the minus v square term here. So, now we need to evaluate the electric field components tangential to the air dielectric interface, because we have to find out the values of A and B. In order to find out the values of the unknown constants A and B, we need to evaluate the tangential electric field components and the tangential magnetic field components at the dielectric air interface. So, for that purpose we write for mod x less than a by 2, which is inside the dielectric strip, we have E z as a by j omega epsilon d k d square minus k z square sin u x e to the power minus j k z z. This is directly from equation 5 and equation 4. So, that can be written as a by j omega epsilon d, because k d square minus k z square is u square. So, we can write this as u square sin u x u x e to the power minus j k z z. Since k d square minus k z square is u square from 7. So, we call this equation 8. Similarly, the tangential field component H y in the dielectric or inside the dielectric for the odd mode becomes minus del psi d O by del x, that is minus A u cos u x e to the power minus j k z z. We call this equation 9. Okay. So, this completes the fields inside the dielectric. So, we will continue next with the fields in the air region. Let us pause here.